Good morning. Assalamualaikum everyone. Okay, good morning. So we have 4 students in class. Thank you for coming. Student in Teams, can you hear me?
Yes, miss.
Okay, great. Can you see the slide?
Yes.
Okay, good. Now today I will proceed with the heat transfer heuristics. Before I start, is there any question from previous heuristic on the chemical distribution and separation? Clear? Okay, now I proceed with heat transfer in reactors. Okay, we focus on the reactor. To remove a highly exothermic heat of reaction. Okay, this one when your reaction involve highly exothermic reaction. You can consider to use the excess of reactant. Excess of reactant, inert diluent. That means the inert that is diluting the reaction. Okay, or you can use also cold shocks to reduce the temperature of the reactor. Okay, to control the temperature to a safer temperature. This affects the distribution of chemicals and should be inserted early in the process. Okay, so for highly exothermic, it should be incorporated before the process, before the unit op. Okay, here is the the diagram of how excess reactant works. Now here we have A and B is your reactant. A and B is your reactant. So once it goes to reactor, highly exothermic reaction occur. Then the separator, at the separator, it separates your product and the B. So B here being recycled to the inlet feed. That means B now is excess reactant. Okay, in the first, before the process run and you don't have the recycle stream yet, B should be in excess. Okay, then only you recycle them. Once the reaction occurs, separate and recycle the B to the inlet feed, so that you have excess of reactant. Okay, for an inert diluent, in your feed, you have inert feed, or perhaps you have inert in your reactants. Okay, impurities of reactants, you have inert. So once it goes into the reactor, reaction occur, move out from the reactor, okay, flow out from the reactor, separated, then the inert being recycled into the reactor. Inert. Inert diluent means it will dilute the process in order to control the exothermic reaction. Okay, cold shots, when you have your reactor, one of the stream is in cold temperature, in low temperature. Okay, cold feed. So one cold feed, one normal feed, once it goes into the reactor, so the temperature of the reaction or temperature of the process can be controlled. Okay, so there are three alternatives for highly exothermic heat of reaction. You can use excess of reactant, inert diluent, or cold shots. It is not limited to only one. Perhaps you can combine these methods. Okay, each method. Okay, any questions so far? Now, for less exothermic, second heuristic for heat transfer, less exothermic. What you can do, perhaps you can circulate the reactor fluid to an external cooler. You put cooler. Or you can also use a jacketed vessel or cooling coils on the reactor to reduce the temperature. And you can also consider the use of intercoolers between adiabatic reaction stage. Okay, so this one is for less exothermic. Previous one is for highly exothermic. Okay, less exothermic can consider to circulate the reactor fluid to external cooler. Okay, here you put a cooler. Circulate the fluid through the cooler, then you can control the temperature. Okay, this diagram explains the divided stage. Okay, the reaction operation divided into several adiabatic stages with heat removed by heat exchangers placed between stage. So now you separate them into stages. So before it enters the next stage, you cool down first. Go to the second stage. Then let's say if the second stage, you still need to cool down the temperature, put another heat exchanger at the outlet. Okay. Okay, this one, if you need to reduce from high temperature to low temperature, if the temperature change is very big, so you need to do in series. You need to separate them into each stages because you cannot do just one shot of heat exchanger, one heat exchanger. Because why? You need a lot of energy to reduce that big gap of temperature. Okay, first one is high exothermic. This one is less exothermic. Now the third and fourth is for endothermic. Similar concept, but it is vice versa. Exothermic, you need a cold shot. So endothermic, you need hot shots, hot streams. Okay, so for this one, highly endothermic. again, you can consider the use of excess reactant, inert diluents, and hot shots. So in exothermic, it is cold shots. In endothermic, which is at a very low temperature, we supply hot shots, hot stream. Okay, for less endothermic, circulate the fluid to an external heater. Just now it is cooler, now it's heater. Okay, or heating coils. Consider the use of interheaters between the adiabatic reaction stage. Okay, instead of for exothermic just now you put you need to reduce the temperature, you put cooler, now you put heater. Okay, so what I can conclude over here, for heat transfer, you have exothermic, and endothermic. Exothermic, highly exothermic, and low or less exothermic. Same goes with endo, you have high and you have less or low. Okay, what you should do for highly exothermic? You can put excess of reactant, inert diluent, and cold shots, cold stream. Okay, for less exothermic, what you need just now? Circulate the fluid to external cooler. Perhaps you can use external cooler. Cooling coil. Jacketed vessel. And another one is the cooler between stages. Okay, similar to endothermic, still used for highly endothermic, so you should consider the excess reactant, inert diluent, and hot shots. For the less endothermic, external heater. Then heater between stages. Okay, for the high case, both for only for exo, high case, exo and endo, you should include those alternatives before the process. Okay, early in the process synthesis. Any question so far? Yeah. Student in terms, if you have question on your mic, because I put in slideshow, I cannot read the chat.
Yes, just one question. I'm a bit confused on, so for exothermic and endothermic, right? We are both using excess reactant and inert diluent. How would that work actually? I know for exothermic, you put excess reactant to absorb the heat. How about endothermic? How would excess reactant and inert diluent affect it?
Okay, this one will heat up a bit the process. That means to increase the temperature. So you need to know what are the suitable inert that can provide some heat to the process.
Oh, okay. So it depends on the type of inert, right?
Yes, correct.
Okay. Thank you, Miss.
Okay, a student in class, question from Haliza just now. She asked how to determine for the endothermic, how the excess reactant and inert diluent works. Because in exothermic, we know inert diluent and excess reactant will lower down the temperature. So in endothermic, it will increase the temperature a bit. So you will need to choose suitable inert which can heat up a bit the process. Okay, so that's all for the heat transfer. We have 4. Exothermic, endo, high, and low. Okay, now we move to pumping and compression. The last heuristic, pumping compression, where to increase the steam, to increase the pressure of a stream. Increase pressure, pump a liquid, rather than compress a gas. Okay, that is condense a vapor as long as refrigeration and compression is not needed. Okay, before the pumping. Okay, in normal case, in common case, for vapor, if you need to increase the pressure of the stream, consider to condense the vapor into liquid first, then pump the liquid. Okay, the key word over here is to increase the pressure of a stream. Because of the energy required, if let's say vapor, your stream is in vapor, then you want to increase the pressure of the stream. If you compress, it will involve higher energy compared if you use the pump in liquid form. Okay. Here, if you have vapor phase, then condense, change into liquid phase, then pump. Here is still liquid. Then if you need your final product to be in vapor, evaporate back. Okay, because why? The focus is on the operation of the pump and the compressor. It needs a lot of energy and cost to compress the air. Okay, because here compressor pressure will change, temperature will change as well. So energy required over here is different compared to pump. If pump, pressure change. Common pump pressure change only. You need to flow, you need to push the flow to higher pressure, but the temperature remain. Okay. If you compress, pressure change, temperature change. Then this outlet, this trim on the piping design itself, you need to consider a specific type of pipe that can sustain this high pressure and high temperature. Okay. Get the idea why we need to use the pump instead of compressor. Steam, same. So steam is in vapor form, condense first into water, pump it. Let's say you need to move from one location to one location, right? So it is better to pump the liquid rather than compress the steam. Okay, here, this one. Let's say this is water. We pump the water from this tank into new tank. Okay, imagine this is steam. Let's say steam from here, you want to transfer to another unit op. So it is better to condense it into liquid form than pump rather than using compressor. Because the compressor, you will need a lot of energy. The pump itself, they have many types of pump. Okay, in industry, they have many. That's why they have specific supplier for pump. You have the centrifuge pump, vacuum pump, diaphragm pump, stages pump, multi-stages pump. Okay. What? Okay, in what condition you use compressor? It depends to your process. If your process, let's say, highly volatile, so you will need a very low temperature to condense it. Then you might consider to use compressor instead. So you balance out the energy and the costing. Okay, this one, this one should be compressor, not pump, compressor. So I add this slide just to show you how it works. Okay, the working principle of the pump and the compressor. So the compressor, it pulls in the air. Pulls in the air. This one is centrifugal force. It uses centrifugal force. Okay, so the air suck in the air, then it centrifuge inside. Air travels around the casing. Then the air passes a diffuser. It slows and increase in pressure. So here, pressure will be high. Temperature might change as well. Pressurized air is forced through the outlet. Okay, like your water heater, you use pump. If no pump, what will happen? Huh? no water or slow. The flow is very slow, right? So that's why we use the pump to push the flow rate. To push the flow rate. Okay, so when we push, then the pressure change. Okay, I want to share with you one video. One from a supplier website. Okay. Here. This it shows how the air compressor works. Here they suck the air being sucked. Then the piston, when it goes down, it will open up this. When it pushes up, it will open this gate. So pressurized air being released. Okay, so this one is a basic principle of the compressor lah. Yes. Yes. Yeah, it depends to the piston. If you check the properties of the compressor, they have power. So that power input will determine how fast the air will be sucked and be released. Yes. Okay, now we move. Okay, any question? From the teams, any question?
No, miss. Thank you.
Okay, great. Okay, basically this is the mind map of the heuristic. You have 5 of it. Okay, 5. From the slide. Wait, I share the first slide. This one. Okay, you have 5. Chemical reaction, mixing and recycle. This is on the distribution of the chemicals. Then separation. Number 4 is the heat transfer part. Okay, number 5. This one is task integration. Okay, now this one described with the mind map just now. Okay, this is the first part. Second part. Third is the separation. Fourth and fifth. Okay, so here it summarized already the main point over here. For the raw materials and chemicals, what to do. Distribution of chemicals. So these are the heuristics. Okay, separations. These are the heuristics. Heat transfer, the endothermic, exothermic, and the pumping and compression. Okay. Now we are done with the heuristics. There are few other heuristics. Okay, where from here, heuristic 12 to 20, separation involves solid. Okay, now this one focus on the solid. We can use crystallization and centrifugation and others. Okay, multiple effect evaporators. Heuristic 25 to 33, you can use heat exchanger, furnace, all these things. Okay, so this one you can read through. There are many more, so you just pick up the few important things. Okay, we take a break 5 minutes before I start this one. Okay, so we start on the steps in designing chemical process. We have covered this in chapter 1 last time, the steps in product and process design, where we have the initial part, the part 1, part 1 which involve the assess the problem, process creation and development of base case. Process creation, after you select few processes, then you choose the most feasible one, then develop the base case, the basic process, the basic process flow. Okay. Then after that, move to part 2 where you need to detail out the synthesis. What equipment to use, what chemical to use. Okay, then the process controllability assessment. What instrumentation that you need to install? What do you need to control? Okay, for example, for reactor, did you require to control pressure, temperature? Is level important to control or not? Okay, is composition is important to control or not? Okay. Then come out with the detailed design, sizing, cost estimation, everything. After you had done part 1, 2, and 3, then only you can start up your plant. Okay. Now we go into detail each part. Process creation and development base case. Okay. Now for process creation, as we discussed earlier, so I just repeat the similar things where you should assemble data to support the design. Let's say you have been assigned to your PDP is ammonia, right? Ammonia. Then collect all data that is related to ammonia production. Huh? Urea, sorry. Urea. Okay. Urea. So select the data related to urea production. Then from there, experiments over here. That means here you need to choose the best process to produce urea. Okay. Then once you optimize the process. Okay, so sorry, this one is the process synthesis. The one that you need to select the best process. Then from there, come out with the synthesis tree. Okay, the design alternative. Similar to your FYP project as well. Let's say you need to, let's say for adsorption process. So what are the parameters need to identify, need to evaluate? There are many parameters. So modification of adsorbent, there are many processes to modify. So select which one is the best for you. After that, you come out with the development of base case design. Once you select the most feasible process, then from there, develop the base case. Perhaps you can develop a basic process flow. Okay, for example, over here, development, process creation and development of base case using VCM manufacturing. Okay, this one I skip few slides because those slides are repeating from chapter 1. Okay, so that's why I skip up to here. Slide before this slide we have discussed earlier in chapter 1. Okay. Now this is the synthesis step. This one, the important step 5. You will need to eliminate differences in molecular types. distribute the chemicals, and then eliminate the differences in composition, temperature, pressure, and phase, then integrate the task. Okay, we use VCM manufacturing as example, where you have a few possible reactions that can produce VCM. Okay, here listed 5 reaction paths. You can do direct chlorination of ethylene, okay, hydrochlorination of acetylene, thermal cracking of dichloroethane from chlorination of ethylene. This one, thermal cracking from oxychlorination. Okay, fifth one is the balance process for chlorination of ethylene. Now, from these 5 processes, main target is to produce the VCM. Okay, all can produce VCM, but all these reactions has different parameters, different considerations, different constraints, and also different byproduct. This one you have HCl. This one you have water as the byproduct. And the reactant as well. This you need Cl2. These two you need HCl. Okay, so in addition of the O2. Okay, so from these 5, filter out which one is the most feasible. Now, first step is to eliminate differences in molecular type. VCM is common, so you can get the infos from the any references. Okay, so these are the reactants or products produced from your process. We have acetylene, chlorine. Okay, list out all the chemicals involved, whether in reactant or in product. Okay, list out their properties, identify the chemical formula and structure. Next, to select the pathway. List out what is the reaction occur for each pathway. Okay, then list out the advantages and disadvantages. So from there, you can decide which one to be used later. Okay, this one as in general. We are not considering any detailed costing analysis yet, as in general. Okay, as in the infos that you can get. Okay, now advantages, it occurs spontaneously at few hundred degrees C. Spontaneously. So the reaction rate is fast. Disadvantages, it does not give a high yield of VC with simultaneously producing large amount of byproduct. Okay, lower yield, high byproduct. Half of the expensive chlorine is consumed to produce HCl as byproduct. Okay, so from this process, low yield, high byproduct. Next, consider the second process, which is the hydrochlorination of acetylene. Okay, the advantages, higher efficiency, higher yield of the acetylene to VC in the presence of this catalyst. Moderate reaction conditions. Okay, disadvantages, flammability limits. So here, this process, it has 2 advantages. And it produces higher yield. Okay, then we consider the next one. Thermal cracking from chlorination of ethylene. Okay, you react with chlorine first, ethylene, first step, move to second step. Then you'll get your product. Okay, now conversion of ethylene to 1,2-dichloroethene in exothermic reaction is 98% at this condition. Intermediate, spontaneously at 500 degrees C, conversion quite high. Okay, so here the conversion high and occurs at spontaneously 500 degrees C. First reaction, exothermic. The condition is not that high. You see temperature less than 90 degree, less than 100, and at atmospheric pressure only. Okay, so the next reaction at quite high temperature, but occurs spontaneously. Still, the conversion rate is high, more than 50%. Okay, the disadvantages, half of the expensive chlorine is consumed to HCl, the byproduct. So which may not be sold easily. So here HCl is still high. We want byproduct, how to say? We want the main product to be higher compared to the byproduct, right? Okay, next we consider the next one. Thermal cracking from oxychlorination. Here it involves ethylene, HCl, O2. Highly exothermic, achieve 95%. Okay, this one 95% in the presence of this catalyst, followed by pyrolysis step. One pyrolysis as reaction path 3. Now, excellent candidate when cost of HCl is low. So here, cost of HCl is low. Ethylene is your reactant. You need HCl, low cost. Oxygen, low cost as well. Conversion, high. So this might be considered. This reaction might be considered. So the disadvantages, economics dependent on cost of HCl. Okay, now the last reaction, balance process for chlorination of ethylene. Balance process. The advantages, combination of reaction path 3 and 4. The previous one. So all Cl2 converted to Vc. Cl2 all converted into Vc. No byproducts. Byproducts here is just water. Okay, so this one is a combination path 3 and path 4, which is, the 3 is this one. Okay, chlorination of ethylene and oxychlorination. The thermal cracking method. Okay, so from there you can conclude which reaction, which pathway that you can proceed. Okay, here it concludes reaction path 1 is eliminated due to its low selectivity. Reaction 1. Okay, we go back to path 1. What it said just now. Low selectivity. Yes, as it mentioned, the efficiency is not that high. Byproduct is higher compared to the main product. So this one, eliminate. Okay, no need to consider. Then leaves 4 alternatives path. So those 4 perhaps might be feasible. Then you need to compare in terms of gross profit. Gross profit over here, we just compare on the reactant and the products. The price of the reactant and the products only, not considering all the equipment, utilities yet. Okay, so each chemical, list out each chemical, then the cost. Okay, for reaction 2, it involves ethylene. It involves acetylene and HCl. Okay, so each process involves specific chemicals. So we go. Now, reaction path 3, which is this one. Reaction path 3, it involves ethylene and Cl. So list down the properties plus the cost. This is the reactant parts. Okay, reactant. This is on the products part. So product minus reactant. Okay, product minus reactant. Then you get the gross profit. Okay, this one path 3. This is the gross profit that you can get using basis as 1 pound mole lah, 1 pound. Okay. Now move to another pathway. Consider all those pathways. Okay, the gross profit. Okay, once you try to compute, do the same for pathway 2, 4, and 5. Okay, you can try to calculate lah. So from there, you can see which one is more feasible according to the gross profit. Okay, once the calculation done, path 2, you'll see there is negative. So don't bother to proceed with this pathway. You will lose. Okay, so 3, 4, 5, you have some profit. Choose the most profit. So pathway 3 looks like okay, the most profit. Okay, so now we choose pathway 3, this reaction. We create the preliminary flow sheet. Okay, this is the process diagram where you have your input, output, and the reaction occurs inside. Okay, so basically you need to show your input, output, reactions occur. Reactions involved. So if the question asks you to illustrate the process diagram, it should look like this, not the process flow diagram. This one only the process diagram. Okay, the sketch of the general process. Okay, so from here you are clear what to proceed. Next step involve the distributing the chemicals by matching sources and sinks. Source the reactant, sinks are the products, the byproducts. Okay. Next step is to distribute the chemicals. So how can you distribute the chemicals? Again, identify your input and output. Okay, is there any additional chemicals or catalysts required? A conversion of 100% of raw material is assumed. Okay, for first calculation. Then from here, you can see 60% of this one is converted to VCM with a byproduct of HCl. Okay. Distribute the chemicals here means you need to identify how much is your reactant, how much is your input. Okay, whether you need to mix them before or split stream, it depends on how you distribute the reactant into the process and how the product output. Okay, amount of the product output. Okay, so I think I'll stop here. We'll continue next class perhaps on this step 3. Okay, because I need to rush for another class. Any question from the class or from the teams?
No, thank you, Miss.
Cannot hear.
Thank you, Miss. No question.
Sorry, student from teams. Wait, student from teams, I will turn off the mic. Okay, that's all in the teams. Thank you.
Thank you, Miss.
Good, Miss.